Hi everyone, my name is Hansi, and today I will introduce the paper planning ahead in Generative Retrieval, which is a joint work with Chen from Amazon and Zamani from the UMass Amherst, which is my advisor. So first of all, I will introduce what is Generative Retrieval. So Generative Retrieval is a new paradigm for document retrieval. And you represent each document as a unique document ID, which is a sequence of tokens. And then the encoder-decoder model or decoder-only model can be, such as T5, can be applied to generate the relevant document IDs given a query by a constraint bin search. Those in our previous paper published in W.2024 proves that the generative retrieval model can work well on a large-scale data sets, such as MS Markov 8.8 million benchmark. There are several drawbacks of the report. First of all, the report requires very large bin size to perform well. And we know large bin size is not desired because if we use a large bin size, it means that it will increase the number of the LLM calls, and it will be very inefficient. So I will use the figure to illustrate this. So in this figure, we use the MS Markov development set, which is a standard data set for retrieval evaluation. We evaluate the report, we evaluate the performance and the latency of the report on this MS Markov development set. So in the x-axis, x-axis is the bin size, and the y-axis is the performance metric. We use the MR10 as a metric. And the right curve is the performance of the report, and the dashed line in the bottom, it's the performance of BL25, and this is a red line, the red curve and the red line, and the dashed line in the top in red, it's the performance of the report. If we can make the bin size become infinitive, it means that for each query, we can use the report to score all the document in the corpus. And curve in blue is the query latency for our report with respect to different bin sites. So we have two observations. First observation is that report is very sensitive to the bin size. If we set bin size equals 10, it performs worse than the BL25. But if we set bin size as 1,000, then the performance will go up and become one of the SOTA performance. However, if we see the blue curve, the latency curve, when bin size equals 1,000, the latency is very, very bad. We need 5 seconds to process one query on one A100 GPU. This is undesirable. And so people may ask, what's the reason that report needs large bin size? The reason is that the document ID is not perfect. Because document ID is a sequence of tokens. For example, we can say document ID is a length for sequence, and I use a number to represent each token. So in this example, document ID is 1435, right? And if we use constraint bin search to generate the document ID, it means that we will generate document ID token by token from left to right sequentially. So at step 1, we generate token 1. And then step 2 is 14, and step 3 is 143. And then at step 4, which is the final step, is 1435, given the query. And let's assume that we have two documents. Document ID 1 is relevant, and document ID 2 is not, given the query. So even though we can optimize our model very well to make it use the pairwise learning algorithm, to optimize model, to let the model know, okay, document ID 1 should assign with higher relevant score than document ID 2. It's very, very hard to guarantee that its prefix 1 is also can be assigned with high score with prefix 2, because our document ID is not perfect. And because of this, it's very hard to optimize to make sure every prefix of document ID 1 will be more relevant than the prefix of document ID 2. And if we use the small bin size, it means that the prefix 1 might have chance to be discarded. And because we only represent each document, with one document ID. So if the prefix 1 is being discarded, then document ID 1 will be also discarded. And if this relevant document ID got discarded, then our retrieval performance will be very bad, right? And that's the reason why I use large bin size, because large bin size can give us more chance to make the prefix 1 to survive. And if it can survive, then in the final step, we can have the correct ranking to make a document ID in the top. So the question is that how can we solve the challenge, right? So the key point is that we should score or evaluate the quality of prefix in a better way. So what I trying to say is that when we do the sequential decoding, we want the model can more confidently say that if prefix 1 is more relevant than prefix 2, we should conclude, the model should also conclude that the document ID 1 is more relevant to the document ID 2. And based on that, we propose a new framework called planning ahead in generative retrieval. We use PAG to represent it. So the PAG is very simple. It's just based on a very straightforward observation that because we use a constraint bin search. Constraint bin search means that each prefix we generate should be valid. Valid means that this prefix will be finally extended to a set of documents when the decoding step finish. So it gives us an alternative way to evaluate the quality of the prefix based on the final document set. So I will give you the figure to illustrate this. So this is what original constraint bin search work. So let's assume we are in the step I, right? So we have the score for each prefix at step I minus 1. And then we want to expand a new token, right, based on our the prefix at step I minus 1. So we just get all the next token we have, and then combine all the possible combination between the new token score with the old prefix score. And then after we have all of these scores, we just select the top k based on that, right? Based on the new prefix score. And this is the way how original constraint bin search to expand one new token. And because we use constraint bin search, it means that every prefix can finally extend to a document set. So the document set, right? So we utilize this to add a new score to the original. Add a new future score to the original bin score. And the algorithm is very simple. So given each prefix, we can know what's the final document set. And then for this document set, we can compute the document level score in this set with a corresponding query. And then we pick the math score. And we use this math score, we incorporate this new math score to the original bin score. And because we do this generation based on the future, so we call it planning ahead. The future resultant document set, we call it planning ahead. So, and so the other question is that how can we efficiently and effectively compute the document level scores? So to compute this, we just construct a new lexical set-based document IDs to compute this document level score. The set-based means that the token use a backward representation. So the order between token is not important. So we can only call LLM once. Then we can obtain all the document level scores. And lexical means that the token from the for this new document IDs are term-based. Is extracted from the it's a real word extracted from the document. And the reason we use a lexical because that originally our original sequence-based document IDs are constructed based on the semantic-based way. And everyone that's working on IR knows that if you combine the lexical signal with a semantic signal together, your retrieval performance will always be better than before. So we just utilize this this idea to combine lexical document IDs with the original semantic ID to make the system perform better. And because everything is represented as a document IDs, and it can be very easily to end-to-end optimize. And this is the performance, the result table of our model. We conduct the performance on the standard MS Markov 8.8 million passage benchmark. So it's a very large scale data set. So first of all, let's compare our proposed model pack with our with the previous SOTA model's report. So we can find that first of all, in the MS Markov development set, the pack performance is better than the report performance. And second of all, the pack use less bin size, 10 times less bin size compared to the originally report model. And also, if you compare the and people always argue that when you apply the generative retrieval on large scale data sets, the GR model will always worse than the dense retrieval models. But in our work, we shows that compared to like a lot of like SOTA dense retrieval models such as TASB, SIGIR, DRD, if you compare the compare like different standard benchmarks such as standard evaluation sets such as Spark Development, Track 19, Track DL 2020, our report can outperform all of them, the TASB or CRD. So it also shows that our model is a really like a SOTA model on large scale data set. And also for evaluating efficiency things. So we have like our model have two hyperparameters to control efficiency. The first is number of tokens to represent the set-based token IDs. We use M as a representation. And the second is the K, which is the beam size. So we select M equals 64 and K equals 100 as the original setting. And so if we keep M equals 64, even though we decrease the beam size 10 times, right now we only use K equals 10. The performance just drop a little bit. But if you see the query latency, it will decrease from 250 to 44 milliseconds. So it means that first of all, our model is very robust to the selection of the beam size, and second of all, our model can be very efficient. And finally, we do some quantitatively study for our model. So to see the first figure, which is a classing figure, so what we do is we just randomly select 20 queries from the Track 19 dataset, and for each query, we select the corresponding relevant documents. And then, for all of these documents that belong to the same query, relevant to the same query, we think it belong to the same label. And then we use the document ID as a representation to represent each to represent each document. And then we apply the t-SNE. First of all, we apply the classing algorithm, and then we don't apply the classing algorithm. We just apply the t-SNE to make it into the two-dimensional space. As we can see that our document ID are very good because it can nicely cluster the documents with the same relevancy. And see the bottom figure. So in the bottom figure, so remember when we compute the relevance score, so the original way is just use a sequential document ID, right? Which is only use a semantic document ID to compute the score. And the new way is that we combine the semantic document ID with the lexical document ID to compute the score. So the figure here is that for each query, we just get a performance for each query on MS Markov development set or the Track 19 or 20 set. And then we so like for each query we have a score we have the performance score for the new method and the old method. We just compute the difference between them and draw this figure. So from the figure we can find that not all queries are benefit from the combination of the lexical plus the semantic signal. There's still some query that benefit more from the semantic based signal. So this might be the future work I will do. Okay, so yeah.